Welcome to part two of the oxidation reduction reaction series video podcast here at Ontario High School. We are looking at, on this one, balancing oxidation reduction reactions in basic solutions. If you haven't seen the part about acidic solutions, you should pause this one here and go watch that first, because we're going to need that foundation for this particular one. So anyway, welcome, and let's get going. The next two slides contain the rules for balancing chemical equations for oxidation reduction reactions in basic solution. One of the interesting things about this is that the first 7 rules, which will be shown on this slide and the next slide, are the same as when you balance it in acidic solution. So you do the first 7 steps just like you would as if this were in acidic solution. And if you already have those rules written down, you can probably go pretty quickly through this slide and the next till you get to slide 4, which is going to have rules 8, 9, and 10, or steps 8, 9, and 10, that go specifically for what you do after you've balanced it as though it were an acidic solution, but it's in basic solution, so you had better add these 3 steps or you'll be doomed in terms of success. So pause the podcast, write down rules 1 through 7 if you haven't yet. If you've already written them down, just indicate that you do these same 7, and then write down rules 8, 9, and 10 to follow. Here are rules 6 and 7. Again, if you already have these written down, that's no problem. If you have not, certainly pause here and write these down. Well, at last we come to rules 8, 9, and 10 that are specifically for reactions in basic solution. What we're going to do is count the H plus and add equal numbers of hydroxide ion to both sides of the reaction equation. Make sure that you add equal numbers of hydroxide ion, OH minus, to both sides of the equation for every H plus that you have, and you should have H plus just on one side of the equation. Rule number 9, on the side of the equation that you have the H plus and the OH minus, you want to combine them so that you have water. And then for number 10, combine or cancel the water molecules as necessary. Here again is our rationale for writing half reactions. It's useful when balancing to consider the oxidation and reduction reactions, referred to as half reactions, separately. And the reaction we're going to use to demonstrate how to do this in basic solution is the cyanide ion, Cn minus, plus permanganate ion, MnO4 minus, going to CnO minus plus MnO2. So here are the half reactions for the Cn minus plus MnO4 minus yield CnO minus plus MnO2. The Cn minus would go to CnO minus. The MnO4 minus would go to MnO2. First, we're going to balance the atoms other than oxygen and hydrogen. So in the Cn minus becomes CnO minus. We have 1 carbon on each side, 1 nitrogen on each side, so we're okay there. And the MnO4 minus becomes MnO2. We have 1 manganese on each side. And we're going to deal with oxygen and hydrogen separately and last. Next, we're going to balance the oxygens with H2O. So to balance the O on the of the CnO, we add a water to the side of the Cn minus. To balance the 4 oxygens that we have in the MnO4 minus, the MnO2 contains 2 of those, but we'll add 2 waters to the MnO2 side so that the number of oxygens is balanced. Since we've added water to both of these half reactions to balance the oxygen, we now need to balance the hydrogen by adding H plus. So to the Cn minus becomes CnO minus, we're going to add 2H plus to the CnO minus side. And for the MnO4 minus becomes MnO2, we're going to add 4H plus to the MnO4 minus side. For the CnO minus, that's the product side of that half reaction. For the MnO4 minus, that's the reactant side of that half reaction. Now that we've balanced the number of atoms, we need to balance the charge, and we do that by adding electrons to the more positive side to bring the charge on both sides together. So the first thing we need to do is evaluate what our charges are to begin with. For the first reaction, H2O plus Cn minus, that side has a 1 minus charge from the cyanide ion. For the CnO minus plus 2H plus, when you add the 2 plus charges from the H plus the minus charge from the CnO minus, then you get a 1 plus. So one side is 1 minus, one side is 1 plus, and we'll need to add electrons to fix that. For the MnO4 minus reaction going to MnO2, we have 3 plus charges on the MnO4 minus side. 4 plus 1 minus makes 3 plus. The side that has MnO2 plus 2H2O has 0 charge. It's neutral. So we have an imbalance of 3 plus charges there. Okay, so let's see what happened when we go ahead and balance these charges with the electrons. For the Cn minus to CnO minus, we balance the charges by adding 2 electrons to the right-hand side, or the product side of the equation. So we can identify by where we're placing the electrons, which half reaction is the oxidation and which is the reduction. When the electrons are on the product side, that's the oxidation half reaction. For the MnO4 minus going to MnO2, we have 3 plus charges on the left side. We're going to balance that with 3 electrons, 3 negative charges, and that brings us to 0 charge on both of those sides. Now, what we're going to find interesting here is in our oxidation half reaction, we have 2 electrons. In our reduction half reaction with permanganate ion, we have 3 electrons. We've talked about this many times. When you need to balance a 2 and a 3, we balance them by taking them both to 6. So we're going to multiply by a small whole number coefficient that will allow us to get both of these reactions to have 6 electrons in the oxidation and 6 electrons in the reduction. To get the oxidation half reaction to 6 electrons, we're going to multiply all the coefficients in the half reaction by 3. So we'll have 3 times the 1 H2O, 3 times the 1 Cn minus, 3 times the 1 CnO minus, 3 times the 2H plus, and 3 times the 2 E minus. For the reduction half reaction, we'll have 2 times the 3 electrons times the 4 H plus, 2 times the permanganate ion, 2 times MnO2, and 2 times the 2 waters present. As in Dragnet, here's the result of our multiplication. For the oxidation half reaction, we have 3 H2Os plus 3 Cn minus yields 3 CnO minus plus 6H plus 6 electrons. For the reduction half reaction, we have 6 electrons plus 8H plus 2 MnO4 minus yields 2 MnO2 plus 4 H2O. Next, we're going to add the half reactions, canceling the species that are the same on both sides. Notice that we have 3 H2Os on the left-hand side of the reaction and 4 H2Os on the right-hand side of the bottom reaction. So what we'll do is we'll cross out the 3 H2O and leave just 1 H2O on the right. We can cancel our electrons. The 6 electrons that are on opposite sides can be canceled. We have 8 H plus on the left-hand side of these reactions and 6H plus on the right-hand side. So we can cancel the 6H plus and leave 2H plus on the left-hand side of this reaction. I think everything else is non-cancelable, and let's see what that looks like when we do it. Here's what we're left with when we do the cancellations. We have, for the oxidation half reaction, we have 3 Cn minus yields 3 CnO minus. For the reduction half reaction, we have 2H plus 2 MnO4 minus yields 2 MnO2 plus H2O. We add those together, we get 2H plus 2 MnO2 plus 3 Cn minus yields 3 CnO minus plus 2 MnO2 plus H2O. This is really step 7 of balancing as though this were an acidic solution, so that's where we are at right now. Again, once we're done with step 7, we want to recheck to ensure that the atoms in charge are balanced on both sides. We have 2 hydrogens on the left, 2 hydrogens in the water on the right. We have 2 manganese on the left, 2 manganese on the right. We have 3 carbons on the left, 3 carbons on the right, 3 nitrogens on the left, 3 nitrogens on the right. For our oxygen, we have 8 oxygens in the MnO4 minus, and when we go to the other side, we have 3 oxygens in the CNO minus. We have 4 oxygens in the MnO2, and then 1 oxygen in the water. So we have 3 plus 4 is 7, plus 1 is 8 on the right. We have 2 times 4 is 8 oxygens on the left. We balance our charge. 2 plus 2 times 1 minus plus 3 times 1 minus gives us a 3 negative charge on the reactant side of the equation, and we have just 3 times 1 negative charges on the product side, which is equal to 3 negative. So it is balanced for both atoms and charge, and we can now move on to doing what we need to do for a reaction in basic solution. Several more steps are necessary. Step 1 is to add an OH minus to both sides of the equation for every H plus there is on the one side of the equation. So since we have 2H plus on the reactant side of the equation, we're going to add 2 OH minus to the reactant side and 2 OH minus to the product side. For this reaction, now that we've added the 2 hydroxide ions to each side, on the side with the H plus, which is the reactant side, we're going to combine those to form 2 water molecules. And when we look at this then, after we combine the OH minus and the H plus to form the water molecules, that gives us 2 waters on the reactant side and 1 water on the product side. And we're going to be able to cancel those H2O in the next step. After combining the 2H plus and the 2OH minus on the reactant side, we have 2 water molecules on the reactant side. We have 1 water molecule on the product side. We can go ahead and cancel out the 1 on the right and reduce the 2 water molecules on the left-hand side to 1, so that when we have done that, we will end up with H2O plus 2 MnO4 minus plus 3 Cn minus will yield 3 CNO minus plus 2 MnO2 plus 2 OH minus. Okay? When we balance, we look at 2 hydrogens in the water on the left. There are 2 hydrogens in the hydroxide ions on the right. We have 1 oxygen in the water plus 8 in the MnO4 minus, makes a total of 9 on the reactant side. On the product side, we have 3 oxygens in the CNO minus plus 4 oxygens in the MnO2, makes a total of 7, and then 2 oxygens in the OH minus makes a total of 9 oxygens. So our hydrogens and our oxygens are balanced. We have 2 manganese on each side, and we have 3 carbons on each side and 3 nitrogens on each side. So our atoms are balanced. We just need to check our charge. 2 times 1 negative plus 3 times 1 negative makes 5 negative on the left. On the right, we have 3 times 1 negative, and 2 times 1 negative from the hydroxide ions leaves us 5 negative charges on the product side. So the atoms and charge are balanced, so this should be complete. Well, we always do one last recheck to ensure that the atoms and charge are balanced on both sides, and our equation here is balanced successfully. The first 7 steps identical to balancing the equation in acidic solution. The last 3 steps are unique to balancing in a basic solution. Well, we've come to the end of part 2 of our oxidation reduction reaction series dealing with balance equations in oxidation reduction reactions in basic solution. I want to leave you with another quote from the great British statesman Benjamin Disraeli: "A precedent embalms a principle." Think about that one.